Wala ka? Good afternoon. Am I audible? Am I audible? Okay, I'm going to start the session. So today's topic is RLC circuit, DC response, and solution using differential equation. So for this topic, you must have basic knowledge of what is meant by response. So what are all the different types of responses? What is meant by overdamped response, what is meant by underdamped response, what is meant by critically damped response. And before determining the response of RLC circuit, we must know how to determine the response of RL and RC circuit. So if you know how to determine the response of RL and RC circuit, you will be able to understand this concept. Otherwise, it may be a bit difficult for you to follow the session. Okay, I'm going to start now. So here we are going to take a RLC circuit. Our source is DC source, and we are going to see the response and solution using differential equation method. Okay. For that, let us consider a circuit here. You can see there is a switch S here, voltage source, and a resistor, inductor, and capacitor. RLC. This is RLC circuit. Okay. So initially the inductor and capacitor, they are not charged. Before the supply is given, they are not charged, they are uncharged. Okay. So now if we apply Kirchhoff's voltage law, so it's a single loop circuit. So you can assume a loop current I here. So if you apply Kirchhoff's voltage law here, then you'll get this equation. So source voltage V is equal to I into R plus L into di by dt plus 1 by C integral of I dt. So source voltage V, that is equal to algebraic sum of the voltage across the resistor, voltage across the inductor, voltage across the capacitor. So consider it as our equation number 1. Okay, so here we have taken RLC, resistor, inductor, and capacitor. 3 elements are available in the circuit. We have connected switch in between the source and these elements. So initially inductor and capacitor, they are not charged. So if we apply simply Kirchhoff's voltage law here, then you will get this expression V is equal to R into I plus L into di by dt plus 1 by C integral of I dt. Now let us differentiate this equation 1 on both sides. If you differentiate this equation 1, then you will get 0 is equal to R into di by dt plus L into d square I by dt plus 1 by C. So this is if you differentiate this equation, you will get this expression. Okay, so after getting this expression, here simply what I have done in the next step is I have divided both sides with L. So you simply divide both sides with L, or you take L common and send to the left side. Okay, both are same. So simply divide both sides with L, or take L common and send to the left side. So what you will get is that 0 is equal to d square. Yeah. So I have written this term first. Okay. 0 is equal to d square I by dt square R by L di by dt plus 1 by LC I. So in the order of the power of this differentiation. Second order derivative, first order derivative, no derivative at all. Okay. So in that order, I have rearranged the above equation terms and I have written like this. Okay. So I have got a second order differential equation here. So now, in order to simplify it, I'm going to assume d by dt is equal to s. Just to make this above expression more simpler form, in order to convert that into a simpler terms, okay, I'm replacing d by dt with s. So if I replace d by dt with s, okay, so if I replace d by dt with s, so d square by dt square will become s square, okay, into r plus r by l is constant. You can write it as it is. D by dt is nothing but s, so s into I plus here there is no d by dt term, so as it is we will write this term as it is. Okay. So in order to simplify this above expression, I have assumed, this is just an assumption, you can write here assuming d by dt equal to s, or let d by dt is equal to s. You can write like that, and if replace d by dt with s, you will get this expression number 2. So what is this expression? 0 is equal to s square I plus r by l s I plus 1 by l c I. Okay. Now here you can see I is common in all terms. I have taken I common and I have sent it to the left side. So this so you will get, after sending it to left side, of course 0 by anything you will get 0. So 0 is equal to s square plus r by ls plus 1 by lc you will get. So consider it as equation number 3. Okay. So this derivation is bit complicated derivation actually. So you must carefully listen, and it's good if you are simultaneously writing it in your notes, then only you will be able to follow. So now our equation, at last we have got this equation number 3, that is 0 is equal to s square plus r by ls plus 1 by lc. It is a quadratic equation, isn't it? It is a quadratic equation. Equation 3 is a quadratic equation. So you can compare it with the quadratic equation, general equation. What is the general equation? As square plus bs plus c equal to 0. Now, here I have written 3 and here also I wrote 3. 1 second. About next further equations, did I give any notations? I didn't give any notations for to the further equations. So it's better, what I will do is I will write here 4 and I will write comparing equation 3 with 4. Okay, so comparing equation 3 with 4. So what do you get if you compare equation 3 with 4? Here we just see coefficient of s square is 1. So what is a value? A is equal to 1. Okay, a value is 1. Now what is the coefficient of s? It is b. So what is b here? B is r by l. So b is equal to r by l. You can write b equal to r by l. Next constant c. So what is c? C is 1 by LC. So you can write C is equal to 1 by LC. Comparing the quadratic equation that we have got in terms of x with the general equation, we have got these values A, B and C value. Now we can determine the solution of the above equation. That is our equation number 3, not 2. It's equation number 4. Okay, so I hope you know how to determine the solution for the quadratic equation. This is the formula. So you will get two roots, s1, s2 are two roots, S1 S2 is equal to minus b plus or minus root of b square minus 4ac by 2a. So what is, you know what is b, what is a, and what is c? Just substitute all those terms here. You will get this expression. Okay, this is what you will get. So S1 S2 is equal to minus r by l plus or minus root of minus r by l square minus 4 into 1 into 1 by LC whole divided by 2 into 1. So this is what the expression that you are going to get for the solution to determine the roots, we can say. Okay. So these are the roots. So you can further simplify, and you can write like this: S1 S2 equal to 1 by 2 into minus r by l plus or minus root of r by l whole square minus 4 by LC. Okay. So now multiply 1 by 2 within this brackets. If you multiply, you will get S1 S2 is equal to minus r by 2l plus or minus root of r by 2l whole square minus 1 by LC. That's what you are going to get if you send this 1 by 2 within this brackets. Okay. So, I hope you are able to follow because you must have minimum basic knowledge of mathematical simplification. Otherwise, you won't be able to follow. So these roots S1 S2 equal to what now? It is equal to minus r by 2l plus or minus root of r by 2l whole square minus 1 by LC. Now let us consider r by minus 2l, r divided by minus r divided by 2l, I can say, as replace. Let us assume it is denoted by some alpha, and this whole term which is within this root, it is denoted by some beta. Okay, so we are just replacing with some notations here, that's it, nothing else. So if you replace with some notation alpha and beta, so you can write these roots as S1 S2 is equal to what? Alpha plus or minus beta. So I can say in simple words that S1 equal to alpha plus beta, S2 equal to alpha minus beta. Okay. So S1 equal to alpha minus beta and S2 equal to alpha minus beta. Now let us consider some cases. So just consider this term which is within this root. Within this root term, what is there inside the root? R by 2l whole square minus 1 by LC. Okay, r by 2l whole square minus 1 by LC. So let us consider first case. Let us assume, okay, let us assume that r by 2l whole square is greater than 1 by LC. Okay, let us consider. Okay, so they are not the numerical values, isn't it? They are theoretically, we have written r and l and c, but we don't know the numerical values. If we have the numerical values, we can easily tell which term is greater than which term is greater and which term is lesser than the other one, or whether both the terms are equal. Okay, so here we don't know, so we are just assuming that r by 2l whole square is greater than 1 by LC. So if that is the case, then these roots, what are the roots? S1, S2. Roots are real and unequal. Okay, so if r by 2l L square is greater than 1 by LC, then the roots are real and unequal, and such response will be an overdamped response. Where's my cursor? Yeah. Such response is an response. Response means output is overdamped response. Overdamped response means they will never reach the final value. The response will be always less than the actual response, we can say. Okay, response will be overly damped. Okay, so that's why I told you at the beginning that you must have the knowledge of different types of responses, whether they are overly, what is meant by overly damped response, under damped response, and critically damped response. You must have the knowledge. 1 second, you just look at the response here. You see I current with respect to time. You can see it's just for namesake. I'm showing you here the response. So this is the overly damped response look like. Okay. So the response will be response. Here our response is what? Current, isn't it? We are giving supply, and because of the supply voltage, current I flows. So I is our response. So the I is the overly damped response. Okay. So if the response is overly damped response, and if the roots are real or unequal, then the equation 2 will become S minus alpha plus beta into S minus alpha minus beta into I equal to 0. Okay. So if the response is like this, then the equation 2 will become S into alpha plus beta into S minus this is infinity. You have got the roots here, you can substitute the roots in the above equation, quadratic equation. Okay, this is how we will write. I hope you know how to write this equation. Okay, now, so this two you will get this equation 2 becomes like this. So you can write the solution of the above equation. Solution I equal to C1 into e to the power of alpha plus beta t plus C2 into e to the power of alpha minus beta t. Okay, so you must know how to write the solution of the equations also. Okay, so now earlier we have assumed R by 12 whole square greater than the 1 by LC. Now let us consider second case. Let us assume R by 2L whole square is less than 1 by LC. Now if suppose R by 2L whole square is less than 1 by LC, then the roots S1 and S2 will be complex conjugate. Complex conjugate means what? I'm unable to write. Complex conjugate means if one root is A plus JB, this is B. I wanted to write B, but my cursor did not support me. A plus JB, another root will be A minus JB. This is A.
గ్యాస్ ఫామ్ అవుతుంది శనక్కాయలే కదా.
So another root will be A minus JB. Another root will be A minus JB. Okay. So complex conjugate. If the roots are complex conjugate, this is how the root should be. I have written here A, but you can take any other notation. Okay, and the response will be under damped response. So under damped response somewhat looks like this. Okay, so I can draw one more response. T, and this is I. Response will be this dotted line I can put, and this will be your final value, 100% value. This will be your 100% value. So under damped response you will get if the roots are complex and conjugate, and if the response is under damped. So now the equation 2 will become more complex conjugate. You can write S minus alpha plus J beta, S minus alpha minus J beta into I equal to 0. So equation 2 will become like this. Okay, so S minus alpha plus J beta and S minus alpha minus J beta into 1 equal to 0. So this is how the equation 2 is to be written. Now solution. Solution of the above equation is I equal to e power alpha t C1 cos beta t plus C2 sine beta t. This is the solution for the above equation when the roots are complex conjugate and the response is under damped response. So this topic is not a simple topic, so you must be more attentive and try to understand. So now in third case, let us assume that R by 2L whole square is equal to 1 by LC. Okay, it is equal to 1 by LC. So then in such case, the roots for the quadratic equation, they will be real and equal, and the response will be critically damped response. So critically damped response, this is the critically damped response. Okay. So this is a critically damped response. So how will be the roots? Real and equal. Real means there will not be any imaginary terms and they are equal. So equation 2. So if means if S1 is sorry, this is 1. Okay, S1 is A, then S2 will also be A. Okay, if S1 is A, then S2 will also be. If S1 is A, then S2 will also be A. So both will be equal and they will be real terms. So that's why equation 2 will become, you see here what I have written here, S minus alpha, S minus into S minus alpha into I is equal to what? 0. Okay, this is our equation 2 now. Now solution of this above equation 2 is, one second, with equation 2 or 3? This I have assumed as 2 and this is equation 3. So yeah, so I have changed earlier equation 2 and 3, so this is not 2. In case 1 also it was equation number 3. I changed the notation numbering, but I forgot to change here. This is equation number, the equation, which equation? I'll show you the equation. This is our quadratic equation here. This is it. This is the quadratic. This is the quadratic equation. Okay, this is the quadratic equation, equation 3. Here also, in the next case also, this is in this case also. So I think there is no need to write that equation number 2 which I have written in the earlier case. So this is 3. Okay. So unnecessarily I wrote that equation number 2. This equation number 2, I think this 2 is not at all required. Why? Because I have simply removed this I is common, you can take it out, and I might have written this 3 here. Okay, so it's okay, I have already written and I don't want to delete it, so leave it. So roots are real and equal, so equation 3 will become S minus alpha into S minus alpha into I equal to 0. Therefore, the solution for this equation is I equal to e power alpha t into C1 plus C2 t. So you must know how to write the solution for the given expression. Then only you will be able to understand. You must have the prior knowledge of for the differential equations, what will be the solution. Otherwise, you won't be able to follow this session. Now let us solve a numerical problem, and after that I will conclude this topic. I don't want to mix other topics with this topic. that's why I will, as soon as this numerical problem is over, I will just conclude this session. Okay, because okay, I want to restrict with only one topic for one session. That's why I will conclude as soon as this numerical problem is over. So same circuit which we have discussed in the theory. So it's an RLC circuit. R value is 5 ohms, L value is 1 Henry, C is 1 farad, and a DC voltage source of 20 volts is applied to the circuit at t equal to 0, obtained I of t. Okay, so at t equal to 0, DC voltage of 20 volts is applied to a resistor, inductor, and capacitor. We have to determine I of t. So for that, first of all, we have to apply Kirchhoff's voltage law. Okay, if you want, you can draw the circuit. Meanwhile, I will drink water. I hope you have drawn this circuit. So simply apply Kirchhoff's voltage law to the above circuit. You will get this expression. Okay. So source voltage is 20, that is equal to 5 into I of t. 5 is the resistance value. Okay. 5 into I of t plus L. L is 1 Henry into di by dt plus 1 by C. C value is 1 farad. It's integral of I dt. Okay, I of t dt. Their current in the question they have mentioned I of t. That's why I have written it. Okay, so simple equation. Apply KVL and write this expression. After that same pattern, we have to differentiate the above equation 1 with respect to time. Then you will 20 differentiation of 20, you will get 0, 5 into di by dt plus d square I of t by dt square plus I of t. You will get integration and differentiation will cancel each other. Okay. So after differentiating, this is the expression that you are going to get. After that, I have simply rearranged the terms. I have sent this term to the, I have written it first, and I have sent this term here. Okay, so that's it. I didn't take anything common, or I didn't divide both sides with any term. Simply, I have rearranged the above terms in this equation into, and I have rewritten it. So in my equation 2, 0 is equal to d square I of t by dt square plus 5 di of t by dt square plus I of t I have got. Now again, to make it more simple, I am assuming that d by dt is equal to s. Okay, I am assuming d by dt is equal to s and substitute d by d instead of d by dt, substitute s. Okay, instead of d by dt, just substitute s there. So if you substitute dy instead of d by dt, if you write s, so the equation 2 will become somewhat like this: 0 equal to s square I of t, d square by dt square is there. Okay, d square by dt, so instead of that you write s square I of t, d by dt is there, you write s. So 5s I of t plus I of t. This is what you will get. And you can take I of t common, send to the other side, it will become 0. So 0 is equal to s square plus 5s plus 1, which is a quadratic equation. If you have a quadratic equation, you know how to determine the roots for the quadratic equation. So consider it as equation 3. So I must remember that in the other slides, if I have written equation 2, I have to replace it with 3. So this is our equation 3. This is the quadratic equation. So we have to determine the roots for that equation 3. So s1, s2 is equal to minus 5 plus or minus root of 5 square minus 4 into 1 into 1 by 2 into 1. Okay. So I hope this is basic, what to say, you must have the basic knowledge to determine the roots. I hope whoever is attending this session, they have the basic knowledge of determining the roots for the given quadratic equation. So just simplify it, you will get s1, s2 equal to minus 5 plus or minus root of 25 minus 4 by 2. And consider this term as equation number 4. Okay, I hope in the previous slides 4 was not there. Okay, no, it was not there. So that is our equation number 4. Now we just further simplify 25 minus 4 is 21. You can split this and divide 5 by 2 and root 21 by 2. So minus 5 by 2 plus or minus root of 21 by 2. You have got this equation, and okay, so I have split it, and once again without even splitting with common denominator, I have rewritten. I have written two terms here, both resemble the same thing. Okay, so and I have even determined all numerical values are there, isn't it? All numerical values are there. So I have determined the s1 and s2 values by just simply simplifying it. Okay, so I hope you know how to determine the roots. So one root that I have got here is minus 0.21, and the root that I have got here is minus 4.79. Okay. So let us consider equation number 4. Let us consider equation number 4. If you remember equation number 4, this is our equation number 4. Now consider the term which is inside the root. What is there inside the root? 25 and 4. Okay. If we observe 25 and 4, among 25 and 4, 25 is greater than 4. Okay. Among 25 and 4, 25 is greater than 2. Therefore, roots are real and unequal. Okay, based on the theory that I have discussed, you can easily say that 25, since 25 is greater than 4, the roots are real and unequal. So if the roots are real and unequal, then the response is an overdamped response. And the solution for this response, okay, solution for I of t for when the roots are real and unequal and response is overdamped. So the solution is c1 e to the power of minus 5 by 2 plus root of 21 by 2 into t plus c2 e to the power of minus 5 by 2 minus root of 21 by 2 t. Okay, so I didn't solve this in this first equation. You just solve it, you will get e to the power of minus 2.5 plus 2.29, and for this expression minus 5 by 2 minus 2.5 root 21 by 2, it is minus 2.29. So just mathematical simplification here. Mathematically simplify, you will get expression this expression, that is our equation 5. That is I of t equal to e to the power of minus 2.5t. I have taken minus 2.5 e to the power of minus 2.5t common, and I have rewritten other terms within the brackets. That is c1 e to the power of 2.29t plus c2 e to the power of minus 2.29t. Okay. So this is my equation number 5. Okay. So this concept is not as simple as the other concepts in electrical circuits. So it's a typical concept. So you can't blindly go on solving the given expressions as you wish. So it's not in our hands. We have to follow certain rules and regulations, and we must first of all identify what sort of roots are there and how will be the response. Then only you must write the solution. Okay. So now let us find the C value. Okay. C1, C2 are there here in equation number 5. C1, C2 are there. So we have to determine C1 value and C2 value. So whenever we want to determine the C value, that is arbitrary constant, what you must take into mind, the thing that you have to consider is initial conditions. So here there is an inductor at t equal to 0, current flowing through the inductor will be 0. Okay. So at t equal to 0, as soon as switch is closed. Okay. T equal to 0 plus means as soon as switch is closed, current will be 0. Therefore, substitute that condition in your equation number 5. If you substitute that condition in your equation number 5, what is our equation number 5? This is our equation number 5. Okay, you substitute that condition in your equation number 5. What will happen? You will get 0 is equal to C1 e to the power of 0 plus C2 e to the power of 0. Okay. So you just simplify this, you will get C1 equal to minus C2. Consider it as equation number 6. Okay, after we have to determine C1 value and C2 value. So C1 and C2 are arbitrary constants. Whenever you want to determine C values, you must consider the initial conditions. So you must know the initial conditions first of all. So at t equal to 0, current through your circuit will be initially, no current will flow through the inductor, so I equal to 0. So substitute that initial condition in the equation number 5, you will get C1 equal to minus C2. Now once again go to your equation number 5 and differentiate it with respect to time. If you differentiate equation number 5 with respect to time, you will get minus 0.21 C1 e to the power of minus 21 t minus 4.79 C2 e to the power of minus 4.79 t. Consider it as equation number 7. Okay. Now substitute the initial conditions in the equation number 7. After differentiating equation 5, okay, after differentiating equation 5 with respect to time, now substitute the initial conditions. So substitute here, there is no I term, differentiation term is there, d by dt of I is there, but I is not there, only t is there. Okay, this is t and this is t is there after differentiation. So substitute t equal to 0, you will get e power 0 and e power 0. E power 0 means 1. So what is left over? Di by dt is equal to minus 0.21 C1 minus 4.79 C2. Consider it as equation number 8. Okay. So just take a minute. You just go through the terms that are available here. Try to understand. I will proceed. Okay, now we have got some expression after substituting initial conditions in your differentiated response. I is our response, isn't it? So instead of I might have written I of t, then write I of t. Okay. You can write I of t here, because in the circuit itself they have mentioned, so this is t. You can write, instead of I, you can write I of t, it doesn't matter. Okay, now let us go back to our first expression. First expression, what is the first expression? Equation 1. What is our equation 1? Equation 1 is the equation that we have got by applying KVL to the given circuit. Where is my cursor? Yeah. Equation 1, I will show you the equation 1. What is our equation 1? This is our equation 1. Here, this equation we have got by applying KVL to the given circuit. Okay. So here substitute the initial conditions. Okay, if we substitute the initial conditions, yeah, what will happen? I equal to 0, isn't it? I is equal to 0. So wherever I is there, substitute 0. Okay, wherever I is there, substitute 0. So 20 equal to 5 into I plus L into di by dt plus 1 by c integral of I of dt. Okay, I of t dt was there. Okay, so I of t is nothing but substituting initial condition means substitute wherever I of t is there. Okay, you substitute 0. Okay, t is not there here. Okay, so 20 equal to 5 into 0 plus 1 into di by dt plus 1 by 1 integral of 0 dt. So this whole term will become 0, and this whole term will become 0. What is left over? 20 is equal to 1 into di by dt, means di by dt is equal to 20. So di by dt value is how much? 20 we have got after considering initial conditions. Okay, after considering initial conditions and substituting it in our equation 1. So equation 1 is our KVL equation. So in the KVL equation, when you substitute the initial conditions, you have got some term, that is di by dt equal to 20. This expression we have got. So now we can substitute this equation 9 in equation 8. Okay, if we substitute equation 9 in equation 8, what is our equation 8? This is our equation 8. I will erase all those. Di by dt is equal to minus 0.21 C1 minus 4.79 C2. So instead of di by dt, what I should write? I must write 20. That's it. Substitute 9 in 8. 20 is equal to minus 0.21 C1 minus 4.79 C2. Minus 4.79 C2. Okay. So consider it as equation number 10. Okay. Now substitute equation 6 in your equation 10. What is our equation 6? Go back. So what is equation 6? We might have substituted this earlier, but I didn't substitute. Okay, here itself. Okay, here itself you might have substituted. I didn't substitute that. Okay, so equation 6 is C1 equal to minus C2. Substitute that in your equation 10. So wherever C1 is there, you can write minus C2. So if you substitute that, you will get 20 equal to minus 0.21 C2 minus 4.79 C2. So just simplify it. You will get 20 equal to minus 4.58 C2. C2 is equal to minus 4.366. Okay. You have got some value for C2. Now you know the relation between C1 and C2. What is the relation between C1 and C2? Equation 6. C1 is equal to minus C2. So you have got some value for C2. So what is C1? Here C2 is minus 4.366. What is C1? Plus 4.366. So C1 is plus 4.366. Now substitute C1 and C2 in our equation 5. What is equation 5? Equation 5 is the response equation. This what is I of t? This is our response, isn't it? This is our response. This is our response. Okay. So in this response, we have to determine C1 and C2. So by substituting initial conditions, we have determined the C1 and C2. Now substitute C1 and C2 values in our equation 5. So what is it? What is our response now? I of t is equal to e power minus 2.5 t into 4.33 e to the power of 2.29 t minus 4.3, sorry, Yeah, 4.3 e to the power of minus 2.29t. Okay. So response is I of t is equal to e power minus 2.5t into 4.366 e to the power of 2.29t minus 4.366 e to the power of minus 2.29t. Okay, so this is our response. This is what is asked in the question. Okay, so this numerical problem, after this session, you just once again go through the theory as well as derivation as well as this numerical problem, because if you are learning this concept first time, then it's not easy to understand at one attempt. You have to go through it twice or thrice, then only step by step, if you just write it down in your notes, then only you will be able to follow. Okay, so that's why this is a typical content, so I didn't want to mix up this content with the another topics. That's why I'm taking only one topic in today's session. Okay, I hope maybe most of you whoever is attending this session, the most of you might not be able to follow, but this topic is like this. Okay, we can't do anything for that. That's it. I'll create the Google form and you people can fill the Google form. Fill the Google form and later you can leave. After filling the Google form, you just mention that you have filled and you can leave the session. You can leave or is attending this session. Very few members have attended, it's okay. Okay. So whoever in need of, they will attend. Those who don't want, they won't attend. That's it. Or does it matter? If you have failed, you can leave the session. Okay, I'm concluding. I'm just ending this session.